Okay, so last time we developed the concept of the derivative. Um, so to continue that discussion, just want to do an example that we didn't do last time, which is a very good example. Find the derivative at 0 for f of x is equal to absolute value of x. So can someone tell me how you should approach this? And remember, we only have the limit definition of the derivative, right? We don't really have any rules yet. So let me ask you, do you remember what method do you prefer for the derivative? We mainly did the average rate of change definition. But one that we did early on in the class was the difference quotient. They're both valid. Sometimes one is easier than the other. All right, so what is the average rate of change definition? F prime of 0 is the limit as x approaches 0 of f of x minus f of 0 over x minus 0. In the difference quotient definition, f prime of 0 would equal the limit as h approaches 0 of the difference quotient, f of x plus h, or 0 plus h, 0 plus h minus f of 0 over h. Okay, so which method do you want to do first? Which do you like better? We'll do both, but I guess why don't we do, you want to do the second one first? Okay. Okay, so let's find this limit. Limit as h goes to 0. Now, what is f of 0 plus h? Remember, this is f of x. Yep, just absolute value of h. Good. And then what's f of 0? 0. Okay, so what you're doing is the limit as h goes to 0 of absolute value of h over h. Now, what is that limit? Anyone have an idea of how to approach it? How do you do limits with absolute value? Not plus or minus h, but the plus or minus I agree with. So what led you to the plus or minus? Like, can you describe what absolute value of h over h is? It is definitely plus or minus something. Right. So it's plus and minus something. And so think about it. Plug in something positive for h. What do you get back? Plug in 2 for h, for example. What would you get back? Well, you're also dividing by 2, right? So that's 2 over 2 is 1. Right, absolute value of h, that would be true. So, in fact, you get plus 1 when x is bigger than 0. And then what happens when you plug in a negative? Oh, yeah, so, yeah, for absolute value divided by h, yeah, then it's 1. Yeah, when you plug in something negative, yeah, so you also plug the negative into the denominator as well, right? This time you get 2 over negative 2, and that makes negative 1. So the absolute value part is still positive, right? But the fact that you're dividing by the negative that makes it negative. Does that make sense? Okay, so in this case, what's the answer to the limit? Right, it does not exist. And why is that? Because you look at the limit from the left and the limit from the right. Can someone tell me what the limit from the left is? -1, right? Good, because these are values to the left of 0. And the right limit is 1, because these are the values to the right of 0. And since the left and right limits are different, the whole limit does not exist. Okay, so now let's do the average rate of change definition. Oh, not H. Okay, so what is f of x? It's absolute value of x. What's f of 0? It's 0. So we have absolute value of x over x. And then similarly, as you go from the left, it's -1. And as you go from the right, it's 1. So it does not exist. Yeah, any questions about this? So when you see absolute value, it's a kind of a perfect example where you might need to use left and right limits. So let's think about the graph of the derivative. So first, let's think about absolute value of x. So the derivative doesn't exist here, right? Does not exist at 0. Does it exist anywhere else, the derivative? Where does the derivative exist in absolute value? So let's just like, what's the derivative here? In the range of, what I mean by the derivative, I mean exists somewhere in the domain. So like, let's say this is -2, and this would be 2. So when I say the derivative at -2, I'm saying here. So do you mean in the domain? So, but except for 0, you mean, right? So let's just think first, does the derivative exist here at -2? That's okay. What is the derivative again? Can you describe geometrically what the derivative is? The derivative at a point is, so remember how we first, good, this is slope. Slope of what? Good, of the tangent line. At x equals a. What is the tangent line at like -2, for example? What is the tangent line of absolute value of x at -2? How could you draw it? What would the line look like? Is this the tangent line? Is this the tangent line? No. Yeah, how do you draw the tangent line? So pick any 2 points, and then draw the secant line between them. Now keep on squeezing your secant line closer and closer. What does this limit to? It's a line, right? So what is the tangent line? Well, it's boring. The tangent line is the line itself, because absolute value of x is a line on this side of the graph. It's not almost, it's exactly the same line. So this is the tangent line. So the derivative does exist there, right? Do you know what the slope of this line is? Yeah. So the tangent line for non-curved things are actually the easiest things because, you know, it's the line itself. So it's different than what we usually do. Yeah, so what is the slope of this line? Right, -1 because it's absolute value. So it's -1. And for what values of x is it -1? So just for -2, or are there more values? Yeah, which values are they? Okay, well, how about this line? What is the tangent line for this? Or definitely accept 0. But think about the tangent line for this point here. So the arrow must always point to the right when you do your tangent line, right? It's a +1. So which x values are when the slope is +1, and which values are when it's -1? Correct, negative, not integers, but just negative numbers. Right? It doesn't need to be an integer. And then for +1, yes. Do I have a less than or equal or greater than or equal anywhere? Like, yeah, so I don't have that, for example, because we just showed that the derivative does not exist at 0, right? So we don't include that in our domain. So how do you show that in the picture? They're open circles. Okay, and that's your derivative. That's the derivative of absolute value. And again, the open circles signify the derivative does not exist at 0. Okay, any questions about that? So again, the derivative amounts to really drawing tangent lines if you want to sketch it. Okay, so let's do another sketch. So I have this graph of this function, and let's say I want to sketch what the derivative looks like. Let's do the same thing. So draw the tangent line here. And now tell me, is the derivative positive or negative there? Negative. And can you give a reason why? Like, what makes that a negative derivative? Just like in your own words. Right, the slope is negative. It's like pointing downwards. Slope is negative. Okay, so if the slope is negative, that means in your graph, it should be in the negative quadrants. Okay, but how about like up here? Um, which slope is more negative? The one on the left or the one on the right? Which one is more negative? By more negative, I mean which is further away from zero. So the one on the right, is that closer to zero or further away from zero? Yeah, the blue one is further from zero, right? Because it's pointing down more. More negative. Pointing more vertically down. So how do you represent that in your picture? Well, your point should be further down. Now, if you think about it, it's by this curve, this is curving upward like that. More and more tangent lines that you draw will be pointing further and further down, almost vertically down, but maybe not quite, because it won't be like it's not like an asymptote or anything. So what is happening to the derivative? It gets smaller and smaller in that direction. But let's go in the other direction. What about this tangent line? Is it positive, negative? How does it relate to the one before it? Yeah, so it's negative, so it should be somewhere in the lower quadrant, or lower half. Is it bigger or smaller than, like, do I draw it up here or do I draw it down here? How is its slope in relation to the one before? Down here? Okay, so let's recall, here, let's recall something. Yeah, so the negative can be a little tricky. So that's why I'd like to say kind of closer to zero or further away from zero. Can someone tell me what a line with zero slope looks like? Good, it's horizontal. Yeah, so like this, like y equals a. So when I say, so if something is negative, it means it's pointing down. So the more and more it points down, the further and further away it is from becoming uh, a horizontal line. What is the slope of a vertical line? Yeah, it doesn't exist. So in one way, if you want to think about limits, it's like infinite slope. If you keep on drawing like y equals mx plus b's, if you keep on drawing these, the slope gets bigger and bigger. So you could think of it as the slope is getting larger and larger, maybe towards infinity. So the more vertical a line is, the more infinity it is, right? Like, and so if it's pointing downward in vertical, the slope is closer to negative infinity. If it's upward in vertical, it's closer to positive infinity. And then if it's flat, it's zero. So, so for the one here, it's closer to zero, this line here, because the line is flattening out. And then at zero, it's flat. Is that a little better? Okay, so let's go on the other side. So what happens here? Is it positive or negative? Positive, right. So maybe let's put it here. And then keep on going. Is it positive, negative, and is it bigger or smaller than the one before? Yeah, this one is bigger. So it's like more like it's closer to like a vertical line. So as you can kind of guess, yeah. So as you creep up this line, the tangent lines are getting closer and closer to becoming vertical lines. Now, of course, they'll never be vertical because this is not like an asymptote, right? But the slope is gradually increasing, so that's why um, make it look like this. There's no asymptote or anything. All right. Any questions about that? Okay, we'll do more examples. Okay, let's have this graph, and let's sketch the derivative. Okay. First of all, what does this graph look like? We graphed something that looks like this. It does look like a cube root, but cube root would not have these asymptotes up here. But a cube root does look similar to that. Not sine, but tangent, or inverse of tangent. Correct, yeah. So what we sketch might look something like the derivative of arctan. Okay, so let's start over here and look at this tangent line. Positive, negative, close to zero, far away from zero. Which do you think? So remember, negative versus positive. So positive means it's pointing up, right? Negative means it's pointing down. And zero is flat. So the further away you are from zero means you're pointing more up. Oh, different color. The more you point up, the more it's infinite. So, okay, so let's go back to the picture. Maybe I'll draw that little picture here. So this is zero. This is negative. This is positive. So which one do you think this line is? It looks like zero, but I kind of try to draw in a way where it's not flat, or it's like approaching this line, but not quite touching it. Yeah, it's positive, but it's close to zero. So here's another. If the function is increasing, the derivative is positive. Right? That makes sense. How is it changing? If it's increasing, it's changing in a positive direction. So I know in my picture it's hard to tell that, but maybe it's easier to tell that this thing is increasing. Right? That it's never decreasing. So all the way on this side, though, it's getting closer and closer to a flat line, but it's still increasing. So it's positive, but pretty small positive. So as you start creeping up, what's happening to the derivative? Yeah, it's getting bigger, and it's still staying positive, right? At one point, does it stop becoming? Um, does it stop increasing and starts? Maybe the derivative starts to flatten out again. Yeah, so when it's reaching this asymptote, it's starting to flatten out. So do you agree? Maybe by how I drew it, it's increasing the fastest here. Like the slope is biggest there. So maybe in our graph, it will reach at its maximum here and then start dipping back down. And as you can see, it's not it's never going to become negative, nor is it going to be flat. So I know it's all based on like how you draw it, but um, does that make sense? So if the tangent lines are are not that um, artistic, another way you can say just what is the tendency that the graph is doing? How is the graph tending towards? So in this picture, this is an increasing function, and we can see that it's increasing fast here. Fast increasing. Right? And this one is pretty, it's not increasing much. This is slow increasing. And same thing over here. Slow. This is actually decreasing, right? But it's slowly decreasing. Exactly. The more steep, the higher the derivative. And so that's what this picture means here. The more steep it is, like the more it's pointing upward, the bigger the derivative. I don't really know what is. Maybe you have a better word. If steep means how tough it is, like to climb upward, what's the analog expression for steep downward? I'm not sure if I have a word for that. So there's steep upward versus steep downward. So don't confuse the two, right? So steep upward means it's positive, and steep downward is like negative. Okay, so any questions on this? And is that okay, the picture of the derivative? All right, if not, okay, good. Okay, let's do another one. Okay, what graph does this look like? Yeah, this looks like tangent. So what we sketch might be the derivative of tangent, or maybe close to what it looks like. Now for this one, let's start at 0 and then continue. Okay, this point here. Actually, we can just start from the right-hand side. This down here. How would you describe that? Positive, negative, close to infinity, not close to infinity? Yeah, it's positive and high. Now, as you keep creeping to the left, what is happening to the derivative? So what is this asymptote telling you? Yeah, it's getting bigger. As you get close to this asymptote, think about like the curve is getting closer and closer to being a vertical line. Okay, can someone give me an idea, when is the slope like the smallest? Like as you creep towards the right, when does it become the smallest slope? Yeah, it looks like it's smallest at 0. You know, my picture looks nice. So what's happening at 0? So if it's like the most flat at 0, is it positive, negative? What's happening at 0? Yeah, it is positive. Is the derivative ever negative in this graph? No. Is it ever 0 in this graph? No. Okay, so as you continue on to the right, what's happening to the derivative? It's increasing again. And similarly, it's increasing towards infinity. So let me draw this a little bit better. This kind of looks like that. Okay, so questions about that? All right, let's move on. All right. What graph does this look like? Yeah, this looks like sine. So what we draw will probably be what the derivative looks like. Okay, let's start off. Uh, what is the derivative there? There's actually, here, maybe this is a kind of a good strategy for sketching the derivative. Yeah, it is positive. Here's a good strategy for sketching the derivative. Tell me the points where the derivative is 0. So I'm going to mark these by numbers. Where is the derivative 0? I think it gets flat somewhere, right? This is the peak of the mountain, right? And down here is a peak of a mountain. Yeah, I should draw that. Or not a peak, but a valley of a mountain. So at these points, we know the derivative is 0. Okay, does anybody remember intermediate value theorem? I think you probably seen it in pre-calc. Anybody remember this? Let me just do this on the next page. If not, it's okay. We'll go over it again. I'm just curious what you remember. So if not, it's not a big deal because it is a concept in calculus. Here's my intermediate value theorem. Here's town A, and here's town B. Let's suppose you want to walk from town A to town B. Yes, it's about continuity. Let's say you want to walk from town A to town B. Do you have to cross the river somewhere? Right. To walk from town A to town B, you must cross the river. You have to cross it somewhere. So what is this in math language? Suppose f of x is continuous, and f of a is bigger than 0, and f of b is less than 0. What do you think the statement is based on this picture? If you have one value that's bigger than 0 and one value that's less than 0, what does that tell you about a value that needs to exist? Yeah, it needs to cross the x-axis somewhere. So there exists a c such that f of c is 0. So it has to cross. So why do I talk about this? Is that if these are the only zeros of the derivative, well, all you need to know if it's positive or negative here, and it'll stay positive or negative in that region. So, for example, what is the derivative at 4, positive or negative? In the picture here. What's the derivative at 4? Is it positive or negative? It's negative, right? Because it's decreasing. So what the intermediate value theorem says that, like, a function that's negative in between two zeros will stay negative in between two zeros. Like, it can't cross. If you imagine, like, the derivative will be continuous, right? As you are moving along the curve here, you're continuously changing the slope, right? The slope doesn't just magically jump, except for the absolute value function that did, but this is a nice looking curve. So when you do the derivative here, if you know where the zeros are, it's easy to draw everything else. So in short, draw the zeros first, and then the other parts of the graph will be easier to draw. Identify zero derivative first. Just makes it easier. Okay, so, and then in this region here is the derivative positive or negative? Between 0 and 2, is it positive or negative? The derivative. Positive. Right, and you notice as you get closer to the peak of the mountain, it starts to get flatter. And in this region here, from 6 to 8, is it positive or negative? It's positive, right? And it's increasing because the slopes are getting bigger. Yeah, it's a rough sketch, but what does that graph look like? The derivative graph. Yeah, it looks a lot like cosine. All right, good. What happens if we, what was this? Let's do it again. Let's take what we just did for the derivative and let's find the derivative of that. The derivative of the derivative. It's perfectly fine to do. Okay, where are the zeros of the derivative here? If any? Yeah, bottom of the mountain. Anywhere else? It's harder to see, but like up here, looks like it's zero there. It's like flattening out there. Like it starts out 0 and ends 0. So we could put those in. Is that okay? Okay. Okay, so in between the first and second 0 are the tangent lines positive or negative? So in this region here, is the derivative positive or negative? It's negative, right? It's pointing downward. The function is decreasing. So it starts out at 0, and then as we're decreasing, it gets to a point where it's like the most decreasing, maybe here, and then flattens back out at 4. Now in the second half, is it positive or negative? The derivative. From 4 to 8, yes, it's positive. Because as you come back up, it's increasing, right? So it's kind of poorly drawn, but it's increasing. Yeah, the derivative is the slope, good. And then it comes back to flatten out. Anyone know what this function looks like? Um, This one was sine, right? Right, it's negative sine. It just looks like the flipped version. So we'll do that. We'll show that why the derivative of cosine is negative sine. Okay, so let's think about what this second derivative means. Well, let me sketch each function now. Here's sine, or our first function. Here is cosine, like our second function. And then this one was negative sine, our third one, our second derivative. Okay, think back early on when we started talking about limits. If your function was a function of position, what do you think the derivative means? What sort of function is the derivative? So the derivative means change of position. What physics term is change of position? Yeah. Like, how do you measure? So okay, position / displacement. How do you measure change in displacement or change in position? What, physics term is that? Just literally, like, if this was your function of position, and this measures how far this would measure how far it is from when you from where you started. What does the change tell you? What's going on with respect to time? What is the change in position with respect to time? Not acceleration, that's something else. How does position change with respect to how time changes? Yes, it's velocity. Or speed, if you like that better. Maybe see what I mean? Like, how much is position changing with respect to how time is changing? That is a measure of velocity or speed. So how would you characterize change in speed? That's acceleration. How much faster are you increasing in speed? That is a measure of acceleration. How is speed changing with respect to how time is changing? That's acceleration. So what is acceleration? It measures how the derivative is changing. Okay, so let's think about how do you see the second derivative in your original graph? Okay, so think about the beginning of the graph here. That's the slope. As you start increasing in time, what is happening to the slope? Not go all the way there. Is the slope increasing or decreasing? In this interval here. is the, if you want to say speed, is the speed increasing or decreasing? Remember, the slope with the arrows represents speed. It's decreasing, correct. So that, what does that tell you about the acceleration? Is it positive or negative in this region? Right, it's negative. So even though the speed is positive, right? These are, I mean, in the first part, it's pointing upward. The idea is that from where you start at a really high speed, right? But as you continue on, the speed is decreasing. So does that measure up with our graph? Yes, it does. Right, the second derivative is negative. Now, at some point, I put it there, what is happening to the speed after this point? How is the speed changing in the second half? It's increasing. So what should the second derivative be? It should be positive. So if you think about it, the second derivative, what does it tell you? It tells you what is the shape of your graph in that region. So in this region, the shape looks like this. It has this, the cup is like downward. What is the shape in this region? It's an upward cup. This tells you, this is what the second derivative is. It tells you something about what we'll call, defined as concavity. If the second derivative is positive in a region, I'll say an interval, it is called, it means f of x. F of x is called concave up. If the second derivative is negative in an interval, f of x is called concave down. And this is in that interval. In that interval. Okay, so how can you look on the graph to see if it's concave up or concave down? So what I like to do is kind of trace out the curve below it. And soon as you're about to change in the way you draw, you erase that. Oops, not all of that. So notice that here, once you start here, then you start curving upward. So you can draw little frowny faces and smiley faces. Frowny face is concave down. And the smiley face is concave up. And then at this juncture, the second derivative is 0. Maybe I should reverse the colors because I've been doing positive, negative. Any questions about that? I'm feeling concave down? I'm sorry. Is the math making you concave down, or? I hope not. Yeah, I feel that. It's been concave down lately. Hopefully soon it'll be concave up. All right. So any questions about that? So I mean, we'll touch more about the second derivative later, but I think it's a good introduction. Okay. All right. So now we have a kind of a good understanding about how to graph these things. So let's go back to some more derivative rules. So last time, a lot of what we really did was prove the power rule. Was that the derivative of anything x to the n is nx to the n minus 1. And that's kind of what we established last time. So let's say we want to find the derivative of f of x is equal to x to the 7th plus x. So unfortunately, that's not a power, right? It's not of the form x to the n, right? Because we don't have a rule for two things, right? Not yet. So in order to, think about like as you're developing your calculus, or you're developing what calculus is, you would want to find, you would want to give a rule to what the derivative of a sum is. Yes, it will be 7x to 6 plus 1, but we don't know yet. Don't know yet if the derivative of a sum is equal to the sum of the derivatives, right? There's nothing that's obviously true. But think about like we're founding calculus here. We need to prove that this is true before we can say it's 7x to the 6 plus 1. Okay, so how would you want to prove that? The derivative, correct limits. F plus g of x at x equals a. So one thing you might want, the derivative of a sum, you might want the derivative at each point to exist. Otherwise, you might think the limits might be kind of weird, right? So let's do it. Using the definition of the derivative, its limit as x approaches a of f plus g of x minus f plus g of a over x minus a. So what is f plus g of x? So when you look at the sum of functions, at a point, you evaluate it by taking each function at that point. Okay, so now let's simplify this. So f of x minus f of a plus g of x minus g of a. Why did I order it like this? What would my next step be? What do you see here that looks familiar? I can't factor, right? None of these things are the same. So I can't cancel anything, right? However, let's look at here. Do you see f prime of a and g prime of a anywhere? This looks a lot like f prime of a, right? And this looks a lot like g prime of a. Right, we separate them. Right, we want both of them under x minus a. So if we separate, these separately are exactly f prime of a and g prime of a. So we proved it. What is the derivative of f plus g? F plus g prime of a is equal to f prime of a plus g prime of a. This is great. That means that for the function that we had before, we can do what we might expect to do, right? Would just be to take the derivative of each. And then, as we said, as the chat said before, it's 7x to the 6th is the derivative of the first one, then plus 1 is the derivative of the second one. Does everyone agree with that and understand? So this is called the sum law for derivatives. That f plus g prime of x is equal to f of prime of x plus g prime of x. Okay, great. So that's good. That means that we can solve a whole bunch of other things without having to take a limit definition. Okay, let's do another one. Okay, x sine of x. Well, I run into a similar problem I had with this, right? Here, I didn't know if I could just take the derivative of each, right? Whoa, you did that limit so fast, right? So we don't have a law yet for this. So we would have to do a limit, right? But maybe you don't want to do a limit. Maybe you want to develop a rule that says if you have a product of two things, how to find the derivative of it. So that's what we'll develop. So what is the derivative of fg prime? So we have to at a point. Yes, that will be the rule. So we want each of them to exist. So we need to prove that first. Right? We can't just say it. Okay, so what do? You take a limit. So it's fg of x minus fg of a over x minus a. So this is the limit as x approaches a, f of x g of x minus f of a g of a over x minus a. Now you might say, what do you do now? How can you simplify this? Well, there's nothing to factor. I don't see a f of x minus f of a anywhere. So we do a fancy trick. It's a very nice math trick. So what do I want? I want this to pop out somewhere. F of x minus f of a. And I also want this to pop out somewhere. G of x minus g of a. Does anyone have an idea of how you can force that in there? Like a lot of math is like, if you want something, to exist, an expression, you can always put it in there as long as you obey some of the math laws. So here's what we can do. I want a minus f of a somewhere, but but f of x is crowded by g of x. So what can we do? Let's subtract f of a and then multiply by g of x. Do you see why this would give us an f of x minus f of a? How does f of x minus f of a pop out from here? Because I forced a factor. Not canceled, but factored. So if I subtract f of a g of x, am I allowed to do that? What must I do to compensate for subtracting f of a g of x? I have to do something else. I can't just magically throw in an f of a. Right, I would have to add them to compensate. So this is okay. So what is this doing? All I'm doing is adding 0, right? So now I have f of x, g of x, minus f of a, g of x, plus f of a, g of x. So I'm just adding 0 here. And then my original f of a, g of a. So now you can group them like this. And this is f of x minus f of a. And then factored out g of x. This one is g of x minus g of a. Then factored outside f of a. And this was all divided by x minus a, right? And there was a limit in here. All right, see what we did there? So now this limit is good, right? And why is that? What do you see here that looks like the derivative of f or the derivative of g? Right, the brackets over x minus a, those are the derivatives. So what do you get? So as you bring x to a, you get f prime of a, and then when you plug in a for g of x, you get g of a. So skipping the step, but you split up the fraction, right? And then you have g prime of a, and there's an f of a here. And that's it. So this is equal to fg prime of a. Okay, so any questions about that? So now that we have proved it, now we can use it in our problems. But can't prove anything. We can't do anything before we prove it. This is called the product law. Product law. Or what do you call it? Rule, not law. Product rule for derivatives. That if you have a product of two functions, the derivative is found by taking the derivative of the first times the second plus the derivative of the second times the first. Not the derivative, just times the first. Okay. Now I can't remember if this class or the other class, but did we establish this notation, the d dx? Did we establish what this means? What the symbol means? I like the Leibniz a lot better sometimes. If not, I'll just remind. Take the derivative. Yeah, it's just another symbol for the derivative. Take the derivative. It will become a lot helpful in later stuff. Take the derivative with respect to x. To the variable x. So in this case, I'm treating the derivative like a function that does something to this. So I like it just because it allows me not to have to deal with the primes, because the primes can be annoying sometimes, but I like the d dx a lot. Sometimes just easier. So by the product rule, you take the derivative of the first and then multiply the second. And then you take the derivative of the second thing in your product and multiply by the first. So do you see how these are the same? Yeah. When we do implicit differentiation, this will become invaluable. So everyone agree that these two are the same thing? So the f prime means the derivative of. Okay, so let's do it. What's the derivative of x? What's the derivative of x? 1. Yep, that's by the power law. And then there's a sign here. And then the derivative of sine we had established a while back. I think the last time we said what it was. It's cosine, x cosine. So that's it. So now that we have this this product rule, if we know everything in the product, then we can find the derivative. Okay, any questions about this one? Okay. Okay, let's just to add to our repertoire of derivatives, let's find the derivative of cosine. So, so if we recall how we found the derivative of sine was by the difference quotient. So let's do the same thing for cosine. So the limit as h goes to 0 of cosine of a plus h minus cosine of a. Over h. So remember when we did the derivative for sine, we did something similar, right? This is back before we even talked about derivatives, but we had done it. Does anyone remember the sum rule for cosine? Sum angle? Uh, Not quite. It's cosine cosine and then sine sine. You mix it when it's for sine, and it would be plus. It's okay. It's hard to remember. Yeah, so it's cosine a. No, actually, how I remember it is from the double. I remember the double angle formulas more than I do the sum. I have to remember what the double angle looks like, and then that will help me with the sum. Because the double angle for cosine is cosine squared minus sine squared. For some reason, I remember that more readily than the sum angle. And sine 2a is 2 sine a cosine a. So that's how I remember the sum. Like if it's a plus a, then you would get this. That's my personal preference. Okay, so this is the sum angle formula for cosine. So now what? What is a limit that you see here that's a nice limit? What should be jumping out at you? Yes, always sine h over h. Right, since our limit is going to 0, we can just look at that limit. So let's split up this fraction and take this out to the side. So this is very similar to what we did for sine. So we have cosine a cosine h minus cosine a over h, and then minus sine of a sine of h over h. Okay. So let's focus on the first limit. How do you solve this limit? Remember, your limit is of h. So cosine a is just like a number. Yeah, you can take out the cosine a because there's no h involved. Yeah, the second part will be actually well, with the negative is negative sign of a. We'll do that one at the end. Okay. So do you remember how to solve this type of limit? What's your approach to solve this? Right, so you're right, this is 1 sine of a. Yeah, that should be what you're thinking about. Um, but however, we don't see a sine squared cosine squared. But there's no squared, right? But how would you get a Pythagorean identity with the numerator? You have to do something to get a Pythagorean identity. Have multiply and divide by something. That's a good intuition to go to the Pythagorean identity. Also, this would need to be squared as well, right? Yeah, what was the trick that we did for a similar problem? It's like, what would you need to multiply this by to get some Pythagorean identity? Almost cosine, but maybe a little bit more. Good, yeah, I would want to multiply by cosine h plus 1, right? Because that would give me like a difference of two squares. Just remember that the similar trick we had? So you recognize that if you multiply by cosine h plus 1, then this is the factorization of a difference of two squares. So that's how you get the Pythagorean identity in there. Oh, almost Pythagorean identity. So this gives you cosine squared minus 1. Oh, and then, of course, the divide, of course. Okay, so how do you do this limit now? How do you continue? So if you forget why this, remember this is kind of similar to the conjugate trick for radicals, but it's our, trig version for the conjugate trick. One minus sine squared is cosine squared, you mean? Because this is a little bit different, right? So that is true, but let's do something different. Yeah, I guess you could do that. Here, let's make this easier. Why don't I factor out negative 1? Let's factor out negative 1, and then you get 1 minus cosine squared. And what's 1 minus cosine squared? Yeah, sine squared. Yeah, so just to kind of skip that. So you could replace this by 1 minus sine squared, that's okay. But it might be just more, efficient to make that negative sine squared. Either way is fine. So this is sine squared. Okay, so how do you simplify this limit? What do you see here? That's a nice limit. What should be jumping out at you? Yeah, it's not squared, but why don't you just write it like this? That's fine, right? So you can get one of the signs out of the way. That's fine. Do you see why we can do that? You can get one of the signs out of the way. Okay. So now what? What's the limit? Can you find the limit now? Yeah, what is it? Oh, okay, so what is this limit then? So if you're claiming the whole limit is negative sine, that means this limit is 0. Right, because when you plug in 0, you get 0 over 1 plus 1. Yeah, so it's 0. So that's your answer. So that all was to say that, oops, too big. This whole thing just simplifies down to 0, this left-hand limit. So what's the derivative of cosine? It's negative sine. No, you will not have to prove these. But you need to know that the derivative is a limit. Right? Remember when we did absolute value? You really need to do the limit definition, right? Otherwise, you couldn't do it. So there are examples of problems where you need the limit definition. But, I just don't, just pedagogically, it's not good to just give away info without saying why. Right? So we just have to prove them. Okay. But it's good to see. It's the kind of info where it's like it's good to see once and never again. Yeah, but yeah. I mean, I think it'd be good to know in the back of your head, like, where this comes from. But you don't have to be too active and think about that all the time. But if you tuned out for the last 10 minutes, it's fine. This is in a nutshell, all we really need to know. Yeah, it's fine. Okay, so let's do some more limits based on this newfound information. Let's do d dx of cosine sine. Okay, what rule do we have to use here? Product rule, right? So product rule says that if you have a derivative, if you have a product of two functions, you take the derivative of the first, then multiply by the second, and then add it to the derivative of the second function, multiply by the first. So what is the derivative of cosine? We just established it. It's negative sine. And then what's the derivative of sine? It's cosine. Okay, and so what is this? This is cosine squared minus sine squared. What is cosine squared minus sine squared? If it was plus, it would be 1. They're not the same. It's actually cosine of 2x. And this was a double angle formula. So it's interesting derivative. The derivative of cosine times sine is just cosine of 2x. Oops. Right, cosine 2x. What's derivative of sine squared? So first of all, is there a product here? Yeah. Now there is another rule that we'll establish later that we can use to solve this as well, but I don't think this is easier. Yeah, you can use the chain rule here. But I know some people may not like the chain rule, so we're not doing it yet. Maybe that's next class or the class after. But we can treat it as a product just as well. So derivative of the first times the second, derivative of the first times the second. So this is cosine sine plus cosine sine. Okay, that's 2 of them, 2 cosine. What is 2 sine cosine, or cosine sine? So we'll get more used to these rules, but it's good to remember these double angle formulas. So this is sine of 2x. So the derivative of sine squared is actually sine of 2x, which is Interesting. Yeah, double angle formula. Yeah, this is double angle formula. So sine of 2x is 2 sine cosine. Okay, yeah, I mean, I'm not sure how often it'll pop up on the homework, but I know if I was, like, if we were in person teaching it, or, I would, like, expect you to know that. Like, if I were to make the tests. Okay, so same thing for cosine squared. We get negative sine of x, cosine of x, plus negative sine of x, cosine of x. So this is negative 2 sine of x, cosine of x. So that's interesting. Derivative of sine squared was 2 sine cosine. And then derivative of cosine squared. So this is negative sine of 2x. Okay. Does anybody know why this is true? I'm going to say that what this is equal to. Why is this equal to this? Why is that true? That is true, but there's a reason why that's true. Why is negative sine of 2x the same thing as sine of negative 2x? Why can I do that? Why can I bring the negative inside? Not periodic, but it's another property of sine. Correct, it's an odd function. So if in the unit circle, if you have the angle and it maps, and the coordinate is xy, if you take negative of that angle, what you're really doing is reflecting over the x-axis. So this tells you that sine is odd, and cosine is even. If you don't remember what these things mean, if f of negative x is equal to negative f of x, this is odd. If f of negative x is equal to f of x, that's even. It's a symmetry rules. So odd is symmetric over the origin, and even is symmetric over the y-axis. So notice that when you go from angle to negative angle, the x does not change. So that's why cosine is even. When you plug in the negative, it doesn't change. But the y, it changes, but it changes just to it's negative. So plugging in the negative gives you negative of the original. So either of these two are correct, depending on which you like better. Okay. Any questions on this? So just maybe a little reminder. Like something that can come in handy. It's not necessary for this, but just wanted to remind you. Okay, in the remaining minutes we have, let's do one more. Okay, what do we do here? Sine of x times sine times cosine. Do I have a product law for three functions? Do I need to make a rule for the product law of three functions? Any ideas? The derivative would eventually be 1, but I can't just take the derivative of each, right? So the trick is, well, I want two functions, right? The product rule is the derivative of two functions, or the derivative of a product of two functions. So I need two functions here as a product. So on first glance, it may look like three functions. Right, yeah, so we can just let's take this and treat that as one function. And then let's take this and treat that as a second function. Don't need to multiply and divide. This is fine, right? Now it's first function and second function. So now, what is the derivative? Oh, I see. Yeah, actually, you could do that. I like that. That's neat. Oh, but you would need chain rule for that. So no, not yet. So first you would do, yeah. So just you could do that. X sine of 2x over 2 like that. But we don't know yet how to find the composition of the derivative of a composition. We don't know that. Yeah, so we can take derivative of x sine of x times cosine, then plus the derivative of cosine times x sine of x. However, we need another product rule for the derivative of x sine of x. So that is the derivative of x times sine of x plus the derivative of sine of x times x. Now this whole thing is multiplied by cosine plus, and then we do here, that's negative x sine squared. Okay, since we're like out of time, I'll just finish it out. So this is sine plus x cosine minus x sine squared. So this is cosine sine plus x cosine squared minus x sine squared. So then what you can do here, if you factor out an x, then you get cosine of 2x. And sure, what you could do here is, I like that trick, you can multiply and divide by 2 and make sine of 2x over 2 plus x cosine of 2x. Okay, so that was an example of a triple product, but how do you tackle that is just treat it as two products. So just to give you something to think about, try to come up with a rule to satisfy quotients. So try to find try to develop this rule. And it's very similar to the product. We have to multiply and divide by something. But it's good practice, just for math intuition. So this will give you the derivative of a quotient. But we're out of time, so we'll do that next time. So by doing this, you'll be able to solve this one. I'll give you what the answer is, but so just it'd be good for you to try to do it. And then what you can do is use this to find the derivative of tangent. Anyway, we're out of time. So I'll stick around for any questions, but you're free to leave.